This UAS tutorial video is brought to you by AmericaView, a nationwide consortium for remote sensing education, research, and geospatial applications. This project was supported by a United States Geological Survey grant, and its contents are solely the responsibility of the authors and do not necessarily represent the official views of the USGS. Mention of trade names or commercial products does not constitute their endorsement by the U.S. government. Hello everyone, welcome to our 5-part video series titled Using Small Unmanned Aircraft Systems to Assess Rainwater Harvesting Potential for Urban Multifamily Housing. In this series, we will discuss a variety of concepts and methods utilized in assessing a particular urban area's rainwater harvesting potential while placing emphasis on the incorporation of a small unmanned aircraft system in our data collection technique. This series aims to educate users about the methods employed when using a consumer-grade unmanned aircraft system for aerial data collection. In our series, the model UAS used will be a DJI Phantom 4 Professional. With the data that we acquire via the UAS, we are able to conduct further processing of the images to create high-resolution orthomosaics, digital elevation models, and other related products. For our purposes, this video series will focus on the techniques relevant to deriving the aerial measurements necessary to assess rooftop-based rainwater harvesting applications in urban multifamily housing developments. Obviously, many of the methods discussed in this series can be applied to other related research goals, such as solar paneling or green roofing, or really any other project that necessitates highly accurate aerial data. This series will follow a 5-part structure with each video focusing on a sequential concept and its associated techniques. The first video, which you're currently watching, will both introduce the series as a whole while also delving into what rainwater harvesting is and why we are assessing it. The second video in the series will focus on the laws and regulations that govern the usage of small unmanned aircraft systems in commercial purposes and research. The third video will then discuss the image collection process with the UAS and explain how to properly conduct a UAS flight for data acquisition. The fourth video will contain instructional information on how to process the UAS acquired imagery in photogrammetry software, which in our case will be Pix4D Mapper. The fifth and last video will then detail how to determine the land cover characteristics and calculate the site's rainwater harvesting potential. Together, these 5 videos should illustrate to you how you can easily collect aerial imagery with a consumer-grade UAS and then utilize that data to assess sustainable development techniques like rooftop-based rainwater harvesting, solar paneling, or green roofing. Now, let's get into part 1 of the series, rainwater harvesting. So, when you hear the phrase rainwater harvesting, oftentimes it musters up the image of food-grade barrels attached to residential downspouts as a way to collect water for your garden. And as many of us know, these barrels often overflow in a single storm event and are rarely made full use of by the homeowner. However, this is really no longer the stereotypical case of rainwater harvesting. Today, many stormwater professionals are looking closely at rainwater harvesting as a stormwater management technique that provides various benefits to both the user and the city. Oftentimes, these stormwater professionals implement much larger storage solutions, such as cisterns. But before I go any further, let me first explain what rainwater harvesting actually is. Rainwater harvesting is essentially a physical approach to collecting, conveying, filtering, and storing rainwater that would otherwise infiltrate into pervious ground, evapotranspire, or run off into a drainage system. Instead of letting a significant amount of the rainwater run off and be unused, rainwater harvesting aims to capture those potential losses and put it towards on-site water demands. The systems utilized to facilitate rainwater harvesting can vary from simplistic to highly complex, depending on the particular site of interest. After understanding the basics of rainwater harvesting, we then need to address its importance. Much of its significance stems from the concept's ability to provide an on-site water source. These uses are generally involved in landscaping water needs, like a lawn sprinkler system, or in other gray water applications. Another important benefit of rainwater harvesting is that research actually indicates that RH systems are useful in preventing erosion caused by stormwater flows. As a storm event occurs, there's often a large deposition of rainwater at the beginning of the storm, which can cause heightened rates of erosional impacts on urban streams and other waterways. These impacts are especially noticeable during events of flash flooding that are increasingly common in urban environments. With the implementation of RH systems at a large scale, these storm events' impacts can be lessened in vulnerable watersheds and sites of interest. Since these RH systems have the ability to buffer the erosional impacts associated with flashy storm events, they also can provide benefits to their respective stormwater drainage systems. With erosional deposits consistently creating problems for stormwater management systems, the impact of RH systems can help to prevent some of these erosional deposits from occurring. Now that we understand the benefits of RH systems, we now need to discuss how to actually assess an area's rainwater harvesting potential. For our series, we are interested primarily in rooftop-based rainwater harvesting. Rooftop-based methods generally focus on the usage of a gutter system, which is oftentimes pre-existing, and collecting the rainwater that would normally fall onto a building's rooftop and then turn into runoff. Fortunately for researchers, assessing the potential amount of rainwater to be harvested in a particular location is fairly simple. The key measurement needed in order to calculate the RH potential for a site of interest is the two-dimensional surface area of the rooftops. Using the surface area in combination with other relevant factors like precipitation trends allows the researcher to calculate the average amount of rainfall that can be theoretically collected at that site. And depending on the amount that will be collected, then an accurate decision can be made regarding the storage needs. By incorporating storage vessels that accurately match the amount of rainfall being captured at a site, then more effective use of the water will occur and less rainwater will be wasted. Up next in the series will be part 2, which discusses UAS laws and regulations that are relevant to our research goals and methods employed. In that video, we will discuss two main topics, FAA and UAS laws, and Part 107 rules and test procedures. In these two topics, we will go over all the relevant regulations that pertain to unmanned aircraft systems and their usage in research. Thank you for watching.